Hi everyone, my name is Matt Watson. I'm a software developer on the Keras team, and today I'm going to be talking to you all about Keras Preprocessing Layers. This is an extension to the Keras API that we've been working on the Keras team and across TensorFlow as a whole for a couple of years now. So we're excited to show off what these layers are, what you can do with them, and why they will hopefully make your model development workflows easier. A quick plan for the day. We're going to first talk about motivation, which is really going to be what's the problem we're trying to solve and why are we solving it in the way that we are. Then we'll talk a bit about an overview of every API symbol that we are including with the Keras preprocessing layers. Then we'll use preprocessing layers to make an end-to-end training example, training a model, saving a model. And then the last thing we'll do is show how you could take that training example and distribute it to a multi-worker setting. And that'll be it for the talk. So let's start with motivation. What's the problem that we're trying to solve with Keras preprocessing layers? And I think the best way to really dig into it is to start with an example. So let's imagine you have already collected some sort of data set where you have every input example has a string representing some sort of color name. And you can kind of immediately know strings are not a good input to a neural network. So you're going to need to do some sort of transformation of your color names before you're feeding them into the trainable part of your model. And you need to figure out how to represent your data. And I think at this point, if this was the picture you had given and asked what's the best representation, really the only answer you could have at this point is I don't know. We need to run some experiments. We need to figure out what works and what doesn't work. Here I'm showing a couple different examples of things you could try. You could take your colors and map them to a one-hot encoding, where green will map to a certain index, and you'll get a 1 on that index and zeros everywhere else. And a one-hot encoding is something you could feed directly into a feed-forward neural network. But another totally valid thing you could try is instead use that index to do an embedding lookup, where you're going to map the index that green maps to some number of trainable parameters that will be actually updated and part of your trainable model. And you can use that to then feed into a feed-forward neural network. They're both totally valid approaches. You might have some kind of rules of thumb that you could say here, where if your color space is really small, maybe a one-hot encoding is going to be better. If your color space is really large, an embedding might be more useful. But those are guidelines at best, and really the only way to dig into this is going to be by running experiments, and running experiments where you change kind of your preprocessing and change your feature representation at the same time as you're changing your model architecture. So you can kind of think of when you're developing a model as you're bouncing between these two states of modifying your feature representation, modifying your model architecture, sometimes changing them both at once. And you want to be able to move between those two problems as seamlessly as possible. So one of the issues that you can face when you're trying to preprocess your data is if you're doing your preprocessing in another library or even language, it can be hard to hold the differences in the two libraries that you're working with in your head as you're going about your work. So you end up spending more time figuring out differences between APIs or differences between data formats and not really focusing on the core of your problem, which is how do I represent my features? How should I architect my model? So the idea with Keras preprocessing layers is that Keras layers is an ideal kind of place to give you some tools for preprocessing. So Keras, if you're unfamiliar with the library, will give you a set of layers, which are kind of these Lego blocks that you can use to snap together to build a machine learning model. And that's what Keras has always done. So if we can add another bunch of Lego blocks, basically, that are for preprocessing, you'll be able to assemble your preprocessing transformations at the same time as you're changing your model architecture and really be able to iterate on those two problems without having to context switch between different libraries or frameworks or languages. So that's kind of the hope, is that by making our preprocessing tools layers the same as the rest of Keras, we can really reduce cognitive load and let you focus on the important parts of your problem. Then there's one last thing I should mention here that we're trying to solve with preprocessing layers, which is once you've trained a model and you know it performs well, you'll have your preprocessing, you'll have your trainable model, But generally what you want to do is take all of that and bundle it together before you go actually do inference with this. But when you're going to serve inference with your model, you want to make sure that your pre-processing is performed exactly the same way as it was when you were training your model, which can be hard to get right if you're kind of responsible for zipping all of this stuff together. Because if you make any subtle mistake in the way your pre-processing is applied, you'll get this train-serve skew that can be really hard to detect and hard to fix once you've detected it. So because we're going to be doing everything in Keras layers in a way that really fits naturally inside of Keras, it's going to make it really easy to kind of zip up our pre-processing along with the rest of our model and make one unified model that we can save that can operate directly on our raw inputs. So we talked about our motivation, what's the problem we're trying to solve. Now let's talk about the actual API that we're providing and give an overview of all the symbols in the API. So Keras Preprocessing Layers, this is going to be a set of Keras layers. I think there's 100 or so layers in the main Keras library overall. Keras Preprocessing Layers are going to be about 20 of those 100 layers that are specifically for pre-processing your data. And one thing to note about preprocessing layers, they've been an experimental API inside of TensorFlow for about a year. But as of TensorFlow 2.6, they are now part of the core API and are now a stable API. So before we actually dive into showing all the layers that we've built, I wanted to show what it would look like to build one from scratch, just to kind of convince you of the fact that there's no magic going on here. These layers are just regular Keras layers. So all layers in the Keras library will usually have some notion of configuration, some ways in which you configure how the layers work. The real meat of the layer is going to be a computation graph, which will define how to map some inputs to some outputs. And then sometimes your layers will also have some notion of state that they need to track. So that's true of all Keras layers. Preprocessing layers follow all of these same rules. So we're going to build up here a really simple layer. We're calling it the binarizer layer, which is basically going to take in some inputs, and depending on whether those inputs are less than or greater than a threshold that we're going to define, we'll map them to either a 0 or a 1. So yeah, you can see how this is quite simple to implement in Keras. This takes 5-6 lines of code to write out, where we'll subclass the base Keras layer, and in init we'll define the actual threshold, the kind of configuration to the layer that we care about. And then the call graph, which is defining how we map our inputs to our outputs, is very simple here. We'll just compare our inputs to the threshold, and then just to make sure that we're not going to return a true false value and instead return a 0 or 1, we'll cast that back to a float. And yeah, this is a completely valid pre-processing layer. It's not one that we've included in the library, but it's one that you could write yourself, include in your code, and mix and match with any of the pre-processing layers that we've built for you. So again, this is mainly to show kind of there's no magic with pre-processing layers going on here. They're really just normal Keras layers. There are two things though that it's worth calling out about pre-processing layers. And the first thing is that when we're making a pre-processing layer, we are never going to be allowed to have any sort of trainable weights or parameters inside of them. That's kind of the definition of pre-processing, is this is going to be all transformations to our data that are not parameterized and are applied before training. So whenever we're working on pre-processing layers, there will never be any trainable weights inside of them. And then kind of as a direct consequence of that, we also don't need to worry about making pre-processing layers differentiable. The whole contract with them is we're applying them before the trainable part of our model. So we don't need to worry about being able to backpropagate error terms through these layers. And binarizer layer is a good example here. We're applying this step function where you'd have a tough time getting any meaningful gradients back through this, but we don't need to care. We're not going to be applying this in the middle of our model. This is something that's applied to our data before we do actual training. So we don't need to care about differentiability. So that was showing building a layer yourself. But the goal with Keras Preprocessing Layers is to really try to give you those Lego blocks, those layers that you might need for most common use cases. So now we'll go through and talk about all the preprocessing layers that are built into the Keras library. And there's 3 domains that we're kind of targeting with our preprocessing layers that we're providing. natural language, structured data, and you can think of structured data basically like a spreadsheet where each of your input examples is a different row in your spreadsheet. And for each input example, you have different columns of like strings or integers or floats that you know about each input example. And then the last domain we're looking at is images. So let's talk about all the layers that we're providing for each of these domains. The first thing we'll talk about is natural language, and we have just one Swiss Army knife of a layer here for dealing with natural language, which is called text vectorization. And the idea with how this is going to work is it'll take in your input strings, which can be sentences, paragraphs, or documents in plain text, and it will split that document into a bunch of individual tokens. A simple way to do that is white space splitting, which is being shown here. And then it'll map each of your tokens to a specific index, turning your document into a numeric input that you could then feed into a model. So you'll see this called tokenization, and it's a very common step that you'll want to apply when you're dealing with natural language. So to take a look at what that looks like for in code, we'll show code examples for all of these. You'll have some input data. It's just a string, a tensor string that we're going to pass in. Then we'll create our layer. And like all Keras layers, the preprocessing layers are right in the tf.keras.layers namespace. So we'll make the text vectorization layer there, and we'll pass in some sort of configuration for the layer. For the text vectorization layer, the main piece of configuration it's going to care about is a vocabulary of known terms that will appear in our input data. So in this example, we're saying we know about the, quick, and brown, which you can see will be mapped once we've taken our input, split it into a bunch of words to 2, 3, and 4 in our output. The reason indices are starting at 2 there is because 1, we're reserving as an index for representing words that are not in our vocabulary, and 0, we're reserving as a padding term. So that was natural language. Now let's talk about structured data. Think spreadsheet-like input. And there's kind of two different camps of layers that we have for dealing with structured data. One set of layers we have is all about dealing with categorical inputs. So think strings and integers, discrete inputs of some sort. String lookup, integer lookup, and hashing are all layers that are going to be about mapping your string or integer inputs, which for strings could be any values, for integers could be all over the number line, to a fixed range of integer index outputs. That's what those 3 layers will do. And then category encoding will be about taking these kind of integer indices and doing something like a one-hot encoding that we saw at the beginning of this talk. We also have a couple layers for dealing with numerical inputs, floating point inputs. Normalization is kind of a classic thing that you'll need to do when you're building a deep learning model of some sort, where you want to take all your inputs, you want to rescale them to have mean 0 and variance 1. And then discretization is for actually going from a floating point input to a categorical input by applying a step function to your input values. So to, again, show what these would look like in code, we can define some simple floating point inputs. We'll define the normalization layer and say that we know the mean of our data is 3. We know the variance of our data is 1. If you were to then call that layer on your input data, you'd see that it gets rescaled to have mean of 0. Then the last set of layers that we can look at are all about dealing with images. And again, there's 2 kind of camps of layers that we have for image preprocessing. The first is all about standardizing your inputs in some way. So resizing and center crop are going to be about taking inputs of different sizes and making sure that they're fed into your model at all exactly the same size. Rescaling would be for when you have color channels that go from 0 to 255, you might want to rescale those to go from 0 to 1 before you actually feed them into your neural network. Then we have another set of layers, which I think are cool, that are all about augmenting your data. So these are layers that will apply random perturbations to your images only during training time. And this can be a useful way to make a smaller data set, if you're kind of data constrained, to appear like a larger one by every time you do a different epoch, a different pass over your data, applying different random perturbations. So it can be a good way to train robust models if you don't have that much data. And we have a bunch of layers all about applying different random perturbations to your input. To round out a code example for all of these different domains, you can see here we're going to define some images, a batch of 1600 by 100 images, each with 3 color channels. You can then define a resizing layer, which when you call it on this batch of inputs, will rescale it to have a 32 by 32 image output. So that was an overview of all the Keras preprocessing layers that we provide. There's one last bit of functionality that I should mention that we provide on some of our layers, and that's adapt. So adapt is this utility that we're providing for our stateful layers to learn their state directly from your input data. So we saw the text vectorization layer before needed to have some sort of notion of a vocabulary of all terms that might appear in your input. You can always provide that yourself if you want to, like we did in our example, but sometimes you might want to just learn all the words that appear in your data set without needing to calculate that yourself. So for the text vectorization layer, you can do that by making a layer, calling adapt on your input data, and we'll iterate over every single example in your input data, count all the words, and build a vocabulary for you. You might also do that for normalization, discretization, floating point inputs, where for normalization, you care about learning the mean and the variance of your data. You can adapt a normalization layer over your inputs and learn the mean and variance. So let's take a look at that in code. We'll define some floating point input data, range from 1 to 5. We'll define a normalization layer, and then we'll call adapt on our actual input data. So in that line layer.adapt input data, we're actually going to learn the mean and the variance of our input data and set that as the layer's internal state, so that when you then call it on your input data, you can see it's rescaling our input data to have mean 0, variance 1, without us needing to compute the mean and variance ourselves. The last thing to mention here is that adapt is really intended to be a single machine utility. If you have a huge data set that won't fit on a single machine, and you need to do something that looks more like a MapReduce, where you're only computing statistics on pieces of your data on any given machine, in that case, you really should not be using adapt. That's not what it was intended for. But TensorFlow Transform is another library inside of TensorFlow that's all about handling those really big data use cases. So we just gave an overview of all of the symbols that we have in the Keras Preprocessing API. Now let's build up an end-to-end training example using Keras Preprocessing Layers to hopefully make all of this a little bit more concrete. We're going to be doing this end-to-end training example with the IMD reviews dataset. So if you haven't seen this dataset before, it's just a dataset of movie reviews written by people on IMDb. And our goal is going to be to take in a movie review and learn to predict whether it was a positive or negative review. And we'll be building up this entire example in code. So to start off, we can go ahead and import TensorFlow. We can import TensorFlow datasets. We can load up the IMDb reviews dataset, and we can batch it. So to make it clear kind of what our batches are going to look like, I'm printing out a single batch here, and you can see that we have one input feature for everything in our batch, which is going to be this long string, usually like a couple paragraphs of text describing a movie. And then we're just going to have a label, which is either a 0, meaning this was a negative review, or a 1, meaning this was a positive review. And we're going to try to build our model to be able to predict that 0 or 1. So at this point, we have our data set, we've loaded it up. And again, we're in this place where we know we need to do some sort of pre-processing. We have string inputs. Strings are bad inputs to a neural network. Before we can even think about training a model, we're going to need to do some sort of transformation of these inputs to some sort of numeric input. And one of the simplest kind of ideas you can do when you're working with natural language is a unigram model. You might also hear this called a bag of words model, where the rough idea is we're going to take in this sentence or multiple paragraphs of review. We're going to split it into a bunch of different words. And then at that point, rather than look at the ordering of the words or how prevalent a word is, we're going to kind of throw all of that data out and just look at what words are present and what words are not present in our review. So for every review, we'll have to learn a known vocabulary first over our entire data set of all the terms that we know. But then for every review, we will map the review to a long sequence of ones and zeros, where a 1 means this term was present in our review, and a 0 means this term was not present. So the word movie and bad are going to get a 1 because they're present in our review, and the words good and scary, not present in our review, those would get a 0. So yeah, that's called a multi-hot encoding of this bag of words view of our input. So that's a nice, simple approach that we can take to pre-processing our natural language input. What does that look like using Keras Preprocessing Layers? We talked about before how text vectorization is kind of the main layer that we have for pre-processing text input, and we will use it here. So yeah, to kind of go through this code example line by line, the first thing we're going to do here is we're going to just take our data set, and for now, because we're not actually worrying about our label, we're just trying to pre-process the reviews themselves, we're going to map over our data set and discard the label. Then we're going to make our text vectorization layer. We're going to set its output mode to multi-hot, which is where we're asking for this multi-hot sequence of zeros and ones for our bag of words representation. And we're going to set max tokens to 2,500. And all that's saying is we'd like to learn the 2,500 most popular terms from our input data set. And you'll notice here, unlike the last time I showed this label, we're not going to provide the vocabulary ourselves. We're going to actually use adapt to learn it from our input. So we've set the cap of 2,500 as how many terms we should be learning. When we then call adapt over our reviews for the text vectorization layer, we're going to go through every single movie review in our data set, count all of our words, and make a vocabulary of the 2,500 most popular words in our data set. So then if you were to call this layer that we've just created on a single batch of our input data, you can see that it'll map each of our input features, which was a single string, to a 2,500 long array of zeros and ones, which is our bag of words representation. So that's great. We've now figured out a way to transform our inputs from strings to some sort of numeric input that we could conceivably build a model on top of. So yeah, next thing we will do is build a very simple model here. And to keep kind of clear what's pre-processing and what's the actual training parts of our model, I'm going to define two functions here: preprocess, which will apply all of our pre-processing layers, and forward pass, which is going to be applying all of the trainable layers. Though in this example, just to keep everything nice and simple, we're going to learn the simplest possible model we can here, which is a single linear layer with a sigmoid activation function. So we're just doing a logistic regression on top of our bag of words representation. So once we have those two layers defined, we can build our actual model. And the way I'm going to be building the model here is it's called the functional way of building a Keras model, where you're basically going to define some symbolic inputs. You'll then transform those, and we'll transform them by applying the preprocessing function and the forward pass function in succession, which will transform those symbolic inputs to transformed outputs. And then you build a model from those inputs to those outputs, kind of defining the whole transformation of the model. So once you've done that, you can then just compile your model, tell it what kind of loss function you want to deal with, and fit it, which is going to actually train the parameters of your model by running a bunch of epochs over your training data. So this is actually a complete example. You could run this on the IMDb dataset, and I think already get enough, I think like 85% accuracy, which is not a bad start. And the nice thing is we're able to really do our pre-processing and our training, the forward pass of our model, right together in the same block of code, and kind of dealing with these layers that all operate under the same rules. So we just built up an end-to-end training example. At this point, one of the kind of central premises of what we're trying to do with Keras Preprocessing Layers is going to make it easy to experiment with new ideas for representations of your input features. So let's try that out. Let's try adding a new feature to our pre-processed data before we actually do the training of our model. So one thing you could notice about the one-hot encoding is it has no notion of length. Maybe long movie reviews tend to be angry tirades and tend to be negative. And if that was true with our one-hot encoding where we're only looking at what words are present or not, we've kind of thrown out a lot of important data about how long a review is. So we can try adding in a feature for review length, and to make it a nice input for our data, we can also normalize it so it'll have mean 0 and variance 1. So let's try adding that in. And what we can do here, one of the nice things about using Keras preprocessing layers is you can mix and match it with layers that you're writing yourself or with other operations inside of TensorFlow. So here is a rough proxy for how long a review is. We can use tf.strings.length, which is just going to count characters in the review. And then to make sure that our review feature is normalized, we can use the normalization layer. So here we'll map over our input data set, calling tf.strings.length, which will give us a data set containing just the character counts of each of our reviews. We can define a normalization layer. We can adapt that layer over our review lengths, which will then learn the mean and the variance of normal reviews, their character counts. And then if you were to call this on a batch of data, you'll see we've built this nice feature where if a review tends to be shorter than most reviews, you'll get a negative number. And if a review tends to be longer than most reviews, you'll get a positive number. So we've got an idea for a new feature. If we just flip back to the training code, which is exactly what I was just showing before, and we want to add that feature in, we can do that just by messing with the pre-processing function that we built before. So we're going to do the same thing we did before of applying that text vectorizer layer, which will be doing our one-hot encoding, our bag of words, over our inputs. And then we can also do what we just set up on the last slide, call tf.strings.length, call the normalization layer that we defined to give us a new feature. And then the simplest thing we can do with both of those features is just concatenate them together. The rest of our model can actually stay exactly the same. We can still learn a logistic regression over our inputs. Just now, as opposed to just having a bag of words input, we'll also have a feature in our input that represents the length of a review. We can go ahead and train and fit the model, and that kind of shows how preprocessing layers will make it easy for you to try out new representations for features without needing to go through a lot of legwork or without needing to switch between different libraries or different contexts as you're developing your model. So we've built a complete model. We've tried adding a new feature to it. But at this point, there's a performance issue that we should call out and fix, which is if you think about what's going to be happening as we're going about training our model, we're doing the string preprocessing. And when you're working with strings, that's generally going to be happening on the CPU always. And then you'll be doing your loss and your gradient calculation and your parameter updates mainly on the GPU. And the fact that we're bouncing between those two means there's going to be these frequent gaps in our GPU usage, which we do not want. So this is showing kind of our compute usage over time. And if you think about each train step, basically each batch that we handle, we'll be doing that pre-processing entirely on the CPU, followed by our loss calculation, gradients, all of that, mainly on the GPU. So our GPU is kind of just sitting there while we're doing, every time we're doing our pre-processing, just sitting there waiting for that to finish so it can start doing its work, which is inefficient. Accelerators are generally the expensive part of your training. You want to use them as efficiently as possible. And pre-processing, we talked about it before, it's happening before any of the parameters of your model are applied. It's totally independent of what parameters we've learned. So there's no reason to be doing it in lockstep with the actual parameter updates. Pre-processing is something that we could pre-compute. If we wanted to, 2 months before we did training, we could apply our pre-processing to all of our input data, leave it on disk somewhere, and then when it came time to do the training part of our model, we could read it and do it. So there's no reason to be blocking in the way that we are. What we'd like to be doing is essentially pre-compute each of our batches so that every time our GPU is crunching on a certain batch, we're already on the CPU calculating our next batch of data. We're pre-processing it, we're transforming our reviews to these numeric input features. And this would be a hard problem to solve if we had to do it all ourselves. But thankfully, we have a library, tf.data, which kind of solves this problem for us, makes it really easy to do this, and makes it really easy to make our training very efficient. tf.data will allow us to do this pre-computing of our batches of data, our pre-processed batches of data. The only thing we have to do from the Keras side is really split our big monolithic model into two parts so that we can use the pre-processing part with tf.data and treat the training part of our model normally. So yeah, let's take a look at what that would look like in code. I've brought back our code example exactly as it was before, and now we are going to make some changes so that we're efficiently applying our pre-processing with the tf.data library. So first thing I did here, as I was mentioning before, is we're going to take our one model and we're going to split it into two. The first part of our model has no parameters in it, and it's going to map our inputs to our pre-processed inputs. So it's only applying the pre-processed part of our computation. And then the second model is the trainable bits of our model, which will map from our pre-processed inputs to our outputs. Once we make those two models and we've kind of split things like that, we can then call our pre-processing model inside a tf.data.dataset.map, mapping over our entire input and just applying our pre-processing to it. And we can add this call to prefetch, which is going to do that nice and efficient thing we talked about, where tf.data will attempt to always be calculating on the CPU the next batch of pre-processed data while we're working on a current batch on an accelerator. So you do that, and then you can just compile and fit the trainable part of your model normally. And if you do this, I think it's enough for a 30% increase in training time, which is really nice. And you could even actually go further than this, where if you added a call to cache here with tf.data, you could make sure that the first epoch of your data, you're going to do all this pre-processing, but on every subsequent pass over your data, you'll just read that cached pre-processed data from disk. So you won't even have to go through pre-processing at all on further epochs. So that's great. We've fixed a performance issue in our training, but we talked about earlier how when you want to save and run inference on these models, you generally want to zip your pre-processing up together with the actual trainable bits of your model. So splitting our model, we now want to unsplit our model before inference. So we have this nice convenient thing that's applying our pre-processing followed by the trainable bits of our model and can essentially speak our raw data. So if you've done a split like this, where you've split your model into two parts, you can kind of really easily compose them back together. Here we're taking the inputs of our pre-processing model, we're feeding them through the pre-processing model, followed by the training model, and then we're building a model mapping from those inputs to outputs. If you were to save that and predict with it, you'll then see that you can do the thing that we really want at inference time, which is speak our raw data. So if you take this recombined model and call it on two different sentences, you'll map them to a negative score if it's a negative review and a positive score if it's a positive review, at least if your model is performing in the way that it should. So yeah, that was our complete training example. We've built the model, we added a new feature, we've made it more efficient, and saved it for inference. So the last thing I wanted to show in this talk is really quickly how to take that training example that we just built up and distribute it to a multi-worker training setting. And honestly, the IMDb review dataset, it's pretty small. It's not something that you would necessarily need to go to a multi-worker setting with, but for larger training jobs and larger input datasets, training on a number of different machines together is important. So here, I've brought back our code, same as it was before, and just to keep everything fitting on one slide nicely, I've ellipsized our layer and model definitions, but I haven't changed any way in which the code's working. So yeah, if you wanted to take this to a multi-worker setting, Keras makes it easy to do that, and you can do that with the tf.distribute library, and it would look like these two lines of code change here, where the first thing we're going to do is we're going to define a strategy. There's a number of different strategies that you can use in tf.distribute. Here we're going to use the multi-worker mirrored strategy, which is essentially saying we're going to do training in sync across a number of different machines, where each machine is churning on its own different piece of the input data at the same time. Once you've defined your strategy, all you need to do for Keras is make sure that your layer and model definitions are happening inside the strategy scope. Beyond that, you can keep everything exactly the same. If you were applying your preprocessing with tf.data for efficient prefetching, you can continue to do so. Yeah, that's the only real change that you would need to make to keep preprocessing working in your multi-worker setting. There might be other changes you need to make to your model, switching up your batch size, for example, but in terms of the preprocessing, we've tried to make it as seamless as possible. So in terms of what you should take away from this talk, why you should care about preprocessing layers, again, the fundamental goal with the library that we are building is to make it easy to iterate on your features and your model architecture at the same time, rather than needing to do your features in one language, library, framework, and your model building in another, and needing to kind of spend a lot of cognitive load thinking of the differences between the two. Everything is just happening in Keras layers together, which makes it really easy to flip back between changing what your features look like and changing how your model is architected, and running a bunch of different experiments in quick succession. So that's the main goal with the library, make it easy to change those two things together. Once you have built a model and you've saved it and you're happy it's performing well, an advantage of using Keras layers for your preprocessing is it's really easy to zip up your preprocessing along with the rest of your model and have that saved model speak the raw input data that you care about. So you can build an inference model that can take raw input text, like the example that we worked with. Keras preprocessing should be well integrated with the rest of the TensorFlow ecosystem. tf.data and tf.distribute both work with Keras preprocessing, and it is now API stable as of TensorFlow 2.6 and ready to go. So thanks for tuning into this talk, and we're excited to see what you do with Keras preprocessing layers.